Hi, this is Michael Lozen, and this is my Lab 3 programmable stopwatch component. My partner for this lab is Terrence Hall. This component will allow the user to input a value between 0 and 99 on the 7 switches, numbered 0 through 6 of our board. And upon pressing the start button, it would start counting up at a 1 second increment and display each one of those time values on the 7 segment display. The right 2 displays. Pressing the stop button again would stop the count and hold that value until another start is pressed. We have a reset button, which is the down button. If you hold that, it'll display 0, and upon release it'll display 00 on the segments, and it will not be counting. Upon reaching the programmed value or the switched value, a victory pattern will play, and that will be using a state machine. It will count up from right to left, every other LED, and then alternate between the even numbered and the odd numbered LEDs for our specific component. So let's go ahead and run through some of the code here. So we go ahead and we declare our entity here. Those are the inputs and outputs. Our architecture, we got our constants here. Currently I have it open for testbench, but as far as non-test benching, we would use this 1 Hertz value. Or sorry, this 1 Hertz value, the one that's commented out. This is the one we're using for testbench. More on that later. We got signal declarations here, and then we declare our components here. We have a 7-segment driver, which is the component given to us to drive our 7-segment display. And then we have our LED driver, which we use as a state machine to play our complex victory pattern. So inside here we got the port maps for both the timer display driver and the LED driver. So this maps to 7-segment display and LED driver. And now we've got a convert to int here, which takes the user input on the switches and it will convert it to an integer value. We've got our binary coded decimal converter here, which takes that integer value and finds the 1s and 10s digit of that and converts those to BCD to be sent to the 7-segment driver. So we use the modulus operator, and then we have our constants declared up there, and we just do selected signal assignment for that. Here's the detect press. So it's for the start stop button. Essentially it's going to set start stop to high, start stop enable to high as soon as the button is pressed, and then whenever we release it'll go back down. But it only gives you 1 input pulse because of the wait for release condition. Excuse me. We got our timer here, which it takes our clock and reset as inputs, synchronous process, and it will count up to our count 1 Hertz constant here using the 100 megahertz clock. So this converts it to 1 second, and it iterates the current time every 1 second, and we guard against the current time being a value higher than 99 here. So that way there is no way you can exceed 99 on your to the user output. You can't see it to the human eye. It can't ever exceed 99. And then our mode logic is the last part of the main component here. This essentially takes in a lot of the signals and assigns to different outputs what to do here. So we have our reset conditions to set everything to not active upon reset. And then our synchronous process, or synchronous stuff here. So upon the rising edge, we'll take start stop and say, oh, if I hit start, stop, oh, you got to pause it here, so on and so forth. So it'll drive the timers and the LEDs based on the inputs from start, stop, enable, end, target, current time, clock, and finally reset. So we've got the 7-segment driver. I'm not going to run through it because it was provided to us and we've used it. Everyone's using it. Written by Scott Tippins. We've got our LED driver here, which is our state machine. As I mentioned before, we can see our LEDs turn on every other LED, and that's at a 4 Hertz rate. And that'll climb up until we just alternate between these last two, and it creates a pretty cool looking pattern, as you will see in the video later. But that's only upon LED mode being active. So when LED mode is not active, it'll just be blanked. And the reset will also do that. Another thing to note about this LED state machine is that upon hitting start or stop, it'll stop your animation, blink it again, and hitting start again will keep it going up again. And it'll start it from the beginning. So now we just go ahead and declare the ports here. And then we got the architecture here, and again, I've uncommented the test bench value here, but typically when we program the device, this would be the value we use for 4 Hertz. Here's our declarations of the constants for our state machine. So we can see it resembles the pattern I was showing earlier. And here's the declarations of our states, and they're pretty straightforward. The names make sense as to what we should be looking at, especially in correspondence with our constants. And here's the signals. Again, this code is similar to the one provided to us for the state machine. Just modified it a couple ways. So we got our state register here, reset condition here, blanks them upon reset. Otherwise, for every rising edge of our clock, we iterate to the next state. And then inside the state transition here, we have an LED control variable, which is controlled from the blink rate down here, which we set to 4 Hertz. So inside of here, we got LED control, and a modification we have is to use the LED mode as well to get to our next state. But if our LED mode is low, we always go to blank as our next state. And so we can see we go from blank to load 1 to load 2, all the way up to load 7, and then we go to full 1. In between these two states, we go back and forth. So let's get into our test bench. So for the test bench, we wanted to show full functionality of our component, as well as show a special few end cases. Now you can't show every single possibility here, but we want to show some extreme cases, as well as counting from 0 to 99 and showing just the basic functionalities as well. So we decided to just go ahead and lay out a couple tests we wanted to perform and expected outputs here. We'll dive more into those as we actually go through the simulation. But that's how this entire test bench is structured. We have 8 different conditions that we want to test to, and we'll go through those with the simulation. So inside here we declare our constant, our signals, and our component down here. We port map to our component with the same names. We've got our clock declaration in here. We use 100 megahertz frequency, just like that. Now it is important to notice for all the other parts of this test bench, time is scaled to 1,000 times. So when we go through the simulation, 1 millisecond will be equivalent to 1 second. So we've got our reset driver here, and as I was talking about earlier, we initialized the value of reset to 0 as well. As I was talking about earlier, we basically just took each one of these steps and used that to map each one of our user inputs. So, if reset's not being used, we just wait through that. That's how the first steps are. But for instance, like the third step here, reset's pressed for 5 milliseconds, and then we wait for another 10, so reset's active for 5, and for the last 10 it's not active. And so we go through that. For the reset, we have a button driver for our start stop button, so we can see that. And we have, whenever we want to start stop, for an arbitrary time, I just chose 50 microseconds, so like 50 milliseconds, as if the user just tapped the button, but long enough to where the clock can still recognize it. You know, a human's never going to be able to outspeed a 100 megahertz clock, so long enough to where the clock can recognize it. But just like the last one, we initialize it, and then we go through each of the values here, so we can see when we want to press the button, we do so. And then our switch driver, we're just simulating different values the user can put in for the switches. So we initialize it to 0 for the first case, and put our wait statements in, and initialize it to different values for each time we need to. So now we can get into the simulation. So for our simulation, let me go ahead and zoom to fit, and then I might bring this back and zoom in a little bit so we can see it a little better. Something like that should be good for now. So our first condition is to set the switches to 0, wait 10 milliseconds, and the expected output is to be double zeros on the 7 segs, and LEDs are blank. So as we can see here, I just picked a random time inside of here, but we don't see any signal changes inside of this first 10 milliseconds. We see on the 7 segs, our 1s and 10s are both 0. And then we got nothing on the LEDs for the entire time. And then our next step, step 2, switch is set to 0, start button pressed, wait 20 milliseconds. Our expected output is still zeros on the 7 segments, but victory pattern on the LEDs. And I'll zoom in a little bit more so we can see these first couple steps, which are a little harder to see without it. But we've got right here, we can still see 1s and 10s digit is constant throughout the entire time. But if I expand the LED pattern, and also we can see the start stop button right there, we can see our victory pattern play. So we see the rightmost light up, then we go up, and then we alternate between those two. That should do it for that state. So let me zoom back out. So that goes for 20 milliseconds, and we can see the victory pattern stops upon 30 milliseconds, which is our step 3, which is reset button is pressed for 5 milliseconds, and then we wait for another 10 milliseconds. So we expect the solid 0 on our 7 segment, so only the rightmost will be displaying that. It means only the rightmost anode will be active, or in this case not active because of the logic of that. And then we expect the LED pattern to stop immediately, which we can see it does. And our LEDs will go back to regular double zero. So let's just confirm that real quick. I might have to zoom in a little bit on this one. If we go to anodes, we can see for this it is set to just E, or aka only the right one is active, and our 1's digit is 0, so that's good, and we see our LEDs are 0 for that entirety. Alright, so now we can look at step 4, which occurs at 45 milliseconds. So now we set the switches to 10, and start is pressed, we wait 4 milliseconds, stop is pressed, wait 5 milliseconds, and then reset is pressed for 7 milliseconds, and we wait another 10 milliseconds. So our expected output is we want to see climb from 0 to 4 on our 7-segment display. And then we want to see it stop at the 4 millisecond part, and then for another 5 millisecond it just hold that 4 value. And then we want to see a solid 0 as we did with the reset on the last one, and then 0, double 0 again to show the reset worked. So we can see our start, stop, enable pulse right here, and we can see our 1's digit, our 10's digit is constant 0 for this. Our 1's digit goes from 0, 1, 2, 3, 4, and that's when we have another pulse come in, and it holds that value for the prescribed amount of time. And then we have a reset press here, so we can see our solid 0 and our anodes at the proper state. So E meaning only the rightmost is on there. And then upon that reset, we go back down to double 0. Fantastic. Alright, so the next state starts at 71 milliseconds. I'll read that out for us. Our switches will be set to 9. Our start will be pressed. We wait 4 milliseconds. Stop is pressed. Wait 5 milliseconds. Then we press the start button and we wait 20 milliseconds. And the reset pressed for 5 milliseconds, and we wait another 10 milliseconds. So our expected output for this is we want to count up from 0 to 4, just like we did on the last one. And then we pause for 5 milliseconds at 4. And then we start counting up again until we hit 9. And when we hit 9, the segments are going to stay at 9, and we want to see our LED victory pattern play for the remaining 15 milliseconds there. And then upon hitting reset, we want to see that solid 0 for 5 milliseconds, and then the segments at double 0 for another 10 milliseconds. So let's go ahead and run through this one as well. So we can see we count up to 4 here. That's our first start, stop, enable. Our value is also being computed correctly here. Forgot to mention that for some of the previous states. For instance, for this one, in target is 10, and for this one we have 9. So we can see we count up, start, stop again, so we stop at 4 just like the last one. But this time, instead of hitting reset here, we want to start counting again. And as we can see, we do that. Start, stop, enable is high, so we're counting. And we can see our LED victory pattern plays there upon reaching the value 9. And then we wait, and it continuously plays for this entire time until, as soon as we hit the reset, everything goes back to that reset state we've been over a couple times with the rightmost LED at 0. And then we, after releasing reset, we can see our anodes are still going at that 1 kilohertz rate, or in this case, I guess it'd be 1 megahertz because we scale time. But we're showing double 0, which is the important part. So our next one starts at 115 milliseconds. That's number 6. And so we set our switches up to 90. We're going to press start, wait 100 milliseconds, press stop, wait 10 milliseconds, press start, and then wait another 10 milliseconds. So the expected output for that would be to go from 0 to 90 in 90 milliseconds, and then 90 on the segments with the victory pattern running for 10 milliseconds. And then we want it to just be 90 with no victory pattern playing because we hit stop. And then 90 and the LED runs victory after another 10 milliseconds, and then 90 again with the LED victory pattern running. So we're basically showing the functionality. We can count up to 90, as well as showing that we can start and restart, or stop and restart our victory pattern by pressing the start stop button twice. So as we can see, we are counting up here. We have a start, stop, enable. Our end count value is properly computed to 90. So from here, I'm just going to zoom out and scroll over some. we can see the tens digit value changing at the same rate, which is a good sign for us. And we can see 40, 41, 42, all the way up until we hit 90 over here. And we see from there our LED pattern begins playing when we hit 90. And we also see it stop 10 milliseconds after, which is good, upon hitting the start stop button. And so we have all zeros, it's blanked, we hit it again, and it restarts from the beginning, as we can see. And then we do not hit reset at the end of this one to terminate it, because we're going to look at some higher end cases on the next two. So at 235 milliseconds, 235 is when we start our next state. And that one is we set the switches to a lower value. In this case it's 89, and we're going to wait 15 milliseconds and see what happens. So, and then we're going to set the switches to 99 and wait 10 milliseconds. So we expect that we count upwards because our start, stop, enable is still high, and we're not at the value we need to be at, and we don't expect to see any LED victory pattern. So, let's see. And then we'll hit, upon resetting our, it's going to stop at 99 as well. That's something else we expect. And then we set our switches to 99. It should stop at 99 on its own because we have that condition set in. And then as soon as we set our switches to 99, it will start playing the victory pattern because we did attain our value. And as we can see here, our value gets set here to 89. And so our victory pattern stops playing, and we begin counting up again, and we hit 99, but you know, it's not programmed for 99, so no victory pattern. Our count is still enabled for the entire time, but we don't go higher than 99, which is a good sign. And then we see a victory pattern play upon hitting that 99 value. Good. Alright, so what's our next case going to be? That's our final one as well. We set our switches to 103, we wait 10 milliseconds, and our reset is pressed for 5 milliseconds. And then that's it for the simulation. We expect that our LEDs will be instantly blank so that our victory animation essentially stops playing. And then we're going to stay at 99 because we don't want to count higher than 99 if we can help it. And then we don't see any victory animation. So this basically just shows if the user puts in a value higher than the 99, we're just going to stay at 99, no victory pattern. So we can see that here as well. Right here we have our victory animation stop. Our program value is 103, but no victory animation, no increase from 99. We are constantly 99. And then we hit this reset, which we've been over a couple times. We can see our rightmost anode is on. That's the only one that's on, and they're both at 0. And upon release, everything's at 0. And we can see our count, start, stop, enable, timer mode, LED mode, all of that are gone to 0 upon reset. One more thing I would like to show before I end the simulation part of this video is to just show that refresh rate, to show that we do have our 7-segment display changing which one is on and off, and we'll see that in person as well on the video. But it's always important to check on the simulation before you actually put it into the hardware so you don't run into issues like this. And we can see, you know, we know E is the rightmost, D would be the second one from the right, and F is just blanking all of them because we're not using the other two. So that should do it for the simulation part of this video, and I will see you inside the in-person part of the component. Hi, this is Michael Lozen again, and this is for Lab 3, my partner still being Terrence Hall. So there's my component. There's my face. Alright, so we can show off a couple things of functionality. I'm just going to go ahead and set the value to 4, hit the start button, and we can see it starting to count up. And when we hit 4, there's our LED pattern. It looks a lot better here than it does inside code with just 1s and 0s. And I can hit stop to stop the LED pattern. And I'll hit start and it'll play again. And I'll hit reset. As I hold it, we see a solid 0, which is a lot brighter because it's 100% duty cycle as opposed to the 25% we were having before. Let me just play around with a couple different values. So let's make our count value to 2 here. We see our victory animation flashing. But hey, let's say I want to set it to 6 instead. Oh, alright. Well, we're going to count up to 6. There's our victory animation again. But let's say I want to set it to a lower value. Well, no victory because we're not at the value we programmed it to. And if I hit start again, we count up again. Sorry, I hit stop to stop it, so I can show that again one more time. So let's program it to, let's do 16. And we go up. Let's say we want to do 17. Okay, go up to 17. And now I set it to 1. Oh, so we're going to count up. I'm not going to make you sit through it counting up to all 99 values. I'm just trying to showcase some of the things. But we can see both of the 7 segments work perfectly fine, and we saw that in the simulation as well. I'm going to hit reset here, hold it down, goes back to 00, hit start, victory animation. I think that should cover all the bases. If the simulation didn't cover it, now we can see it in person. It looks cool. All right, thank you.